Hello, this is Module 4, Video 2 on functional groups and electron movement, continued. Inductive effects are based on electronegativity differences, and they help us explain a lot of organic reactivity. If you recall electronegativity trends, I drew out some of the more relevant atoms in organic chemistry, with fluorine being the most electronegative. Nitrogen, for example, here is about equally electronegative to chlorine. Carbon and hydrogen really are about similar, not very electronegative. Inductive effects can help us explain a reaction like this. So if you look at what's on the left and what it ends up being on the right, one would predict that electrons would form a bond here to carbon and displace this bond toward the electronegative bromine. Notice our inductive effects. This is like a pull in this direction, or you could look at it like a push from this direction. In electron arrow pushing movement, electrons typically flow in the same direction. So I would avoid electrons moving toward each other like this. So the result of the arrows I just drew in this reaction are the formation of this bond right here and bromine leaving, and note we have to reassess formal charge. So had you never seen this reaction before and were asked to show what the products were, you might look at the reactants and be able to predict, using this formalism, what the products were or are. So some little notes here. Make sure that your arrows, it's clear where they start, like with this lone pair right here, for example, and exactly where they end. Okay. So if this arrow that I'm on right now had been off, in some other place, it would mean something different. So remember, you're just showing where the electrons are going to and coming from. Reassess formal charges throughout. Watch out for the octet rule for all the atoms that matters for. Eventually, with enough practice, you will save a lot of time by not having to draw all the implied lone pairs and atoms, like hydrogens especially. Here's another reaction driven by inductive effects. We see what the product is, so we're not being asked to show what it ought to be, but the arrows for this reaction clearly show electrons going toward the partial positive carbon and then displacing a bond here up onto the electronegative oxygen, resulting in this product. So I just want to delve into some of this one more time, the last time, a little bit more. Let's pause and think, what are we really seeing with this hydroxide ion in a reaction like this, or similar reaction? So, what is the H? We know that the bond is a pair of electrons being shared. We know what the lone pairs are. What is the H and the O really? What are they really? We sort of overlook what we're really doing here. So if you denote the subatomic particles as proton, neutron, and electron, colored like this, the OH group, drawn down here, is really this. This is what we're dealing with. So the hydrogen, remember, is a proton. Here's our bond. The O symbol is really this, isn't it? That's the O symbol. This right here is really the H symbol. So what we're really looking at and concerned with is the electrons. And those would be the ones that are in the red above. That tells us why this is wrong to draw electron movement, or the result, or how these arrows go, excuse me. A lot of people want to do an arrow like this. because they look at this overall reaction and they say, oh, this hydrogen came from here. So he wants us to draw the mechanism. Here's this hydrogen going to here. But that's not what's happening. That's not what bond is forming, because as we just saw above, that would imply that a proton is going directly toward that oxygen atom and forming, but it can't form a bond, because what is a bond? A bond is a pair of electrons. So that's why that's wrong. Arrows don't just show where atoms are going to or coming from. Arrows show the movement of electrons that govern reactivity, govern and predict reactivity. So the correct arrows for this reaction are in blue here. Bond forming, bond breaking gets us exactly to this bond forming, and the broken bond appearing as an extra lone pair on neutral water. So both of these are water, notice. Because arrows are a system for describing the movement of electrons as they form and break bonds, it gives us a way to predict reactions we have not seen before. Here's a reaction we haven't seen before. Bromocyclopentane and diethylamine, see the two ethyl groups. One would predict that if these two are mixed together, that this reactive lone pair would form a bond to this carbon, because, as you recall from above, we have inductive effects. So this is another reaction governed by inductive effects. That bond forms, but that would lead us to that, which is not what we see over here on the right. So that was a wrong guess, in fact. Let's draw in some implied hydrogens, and I'm just going to go back to make it easier to see. Implied hydrogen here, implied hydrogen here, and here. Let's try this again. What do we see in the product? We see a double bond, and the bromine has left, which means what we really have here, and why you have to get good with implied atoms, is that. So now we can predict using arrow formalism that what is going on here is that a bond is forming here. So that is the hydrogen that the nitrogen has picked up. These electrons lead to the double bond electrons over here. And then bromine is eventually displaced like this. And so I should add at the end here Br minus. So clearly the nitrogen has picked up a proton. This explains the origin of the double bond and the bromine leaving. It's still governed by inductive effects toward the end, right? Remember how close everything is actually together. So don't be deceived that it's too far apart for something like this can happen. The diethylamine floats in, and everything is really close together. It can pluck off one of these adjacent hydrogens. So it's a little bit more advanced example of how you can use your knowledge to predict a reaction that you haven't seen before. Here's one more, a two-step reaction. What's going on here? So double bond, HBr with inductive effects here. And what it forms is this. So the double bond is gone, and an additional hydrogen has been added. So one might predict that because of the inductive effects, because of the need for adding a hydrogen, this double bond swings over sort of like a door opening and forming a bond to that hydrogen, displacing the bromine, which explains why the bromine's off by itself now and negatively charged. That gets us to these two reactants that go on further to react, I should say. Products that go on further to react. The bromine, then, all it has to do is come back and bond and form a bond directly to that carbon, which is a carbocation, a plus charge. There's our new bond, and so there's our final product. So we're going to do some exercises in the worksheet handout that gives you practice trying to show what arrows lead from reactants to products. And with some practice, you'll notice you'll get really good at it. And the other thing to notice is, hey, we didn't have to go and read a whole chapter on reactions of alkenes, right? You know, we're just using our basic knowledge of structure, bonding, inductive effects, and movement of electrons, the way they behave, to predict a reaction and understand it more importantly, or as importantly.